Good morning. My name is Emanuele Di Lorenzo from the Georgia Institute of Technology, and today I'd like to talk about the use of empirical dynamical models to forecast ecological indicators in the California current. And this is ongoing work with a PhD student, Tong Su at Georgia Tech. The first question that I'd like to address is, what is an empirical dynamical model, or EDM? Let's assume for a second that you had a favorite ecological indicators that you want to predict or forecast. In this case, we're picking the Nyctiphanes Simplex, which is a key species in the California current. Now, assume that you were God and you knew or had access to the perfect equation or the perfect dynamic describing this particular system. In this case, this simple differential equation says that the rate of change of the zooplankton is equal to some kind of forcing minus a decay rate with time. Now, if we had such an equation, we could then solve this on a computer, which is what we do, for example, when we solve ocean models or when we run simulations with ocean models. Now, to do that, we would have to discretize the dynamics. That is, we have to write this equation in discretized form for discrete time intervals. So this is a discrete derivatives equals the forcing and so forth. And with this discretized equation, we can rearrange the terms to have essentially a prediction equation for zooplankton, where the future value of the zooplankton is equal to some past value of the zooplankton times a coefficient, plus the forcing times another coefficient. And in fact, these are the coefficient of the discretized dynamics. And in this particular case, we have two coefficients, alpha 0 and alpha 1. So we can rewrite this equation in terms of just the coefficients here, which are listed here for their values. Now, this is essentially a dynamical model and a dynamical approach. But what if we didn't know what the real dynamics of the systems are? Well, in this case, if we had past realizations of, for example, zooplankton occurrences and also the forcing, we could use these past realizations to essentially develop or estimate these coefficients from the actual statistics of the data, and in particular from the statistics of the lag covariance between the zooplankton, for example, today and the zooplankton tomorrow, as well as the forcing today and the forcing tomorrow. This is a very powerful approach that has been used in the climate literature to actually develop empirical dynamical models for climate forecasts. So with this said, then the empirical dynamical model really uses empirical lag covariance statistics, shown here, to estimate the coefficients of the dynamics. So the main point is we don't know what the dynamics are, but we can estimate statistically some coefficients that represent a simple dynamical evolution of the zooplankton. And that's why we call it empirical dynamical model. The empirical is the statistics and the dynamical is the fact that you're trying to estimate these dynamical coefficients. So with that said, let's try to use this model to forecast. And what we're going to try to forecast is the Nyctiphanes Simplex time series. This is the zooplankton. And in the Pacific, this species is known to be sensitive to changes in the sea surface temperature anomalies. And so we're going to use that as the forcing here in this equation. But because, we don't want to use all the sea surface temperature anomalies, we are going to decompose this in principal components. So here I've expanded this equation to include essentially the first 10 principal components of sea surface temperature in the Pacific. And each one of them will have a coefficient that is different. And what are these principal components? In space, these are the EOFs, essentially. So the first EOF looks a lot like the El Nino, and with its teleconnections to extratropics, the NPGO, and some PDO residuals. So with that said, let's actually get along with our prediction exercise. And so here again is the observed ecological indicators of the zooplankton. And what we're going to do is we're going to conduct a series of cross-validated predictions. Now, what does this mean? Well, here we have in the model some coefficients that we have to estimate. And the cross-validation, what that really implies is that the data statistics that we use, that are used to derive the coefficients, these guys over here, do not include the data that you're trying to predict. In other words, you're trying to predict data, but the model training has never seen that data. So that in some sense, this is a more realistic estimate of the skill. The cross-validation approach ensures that our forecast skill is not the result of overfitting the coefficients of the data, especially in cases where we are forecasting a single indicator using multiple forcing functions. So with that said, let's go back here and look at the ecological indicator, and let's start with our predictions. And we'll start with a 1-year prediction, which is shown here. So what is shown in the red line are the 1-year predictions. Each of these red asterisks is an independent prediction at 1-year lag, or 1-year lead in this case. And so you can see that overall the prediction scale of this model is quite high with a correlation of 0.8. So that's pretty satisfactory. And it makes sense because this particular time series of zooplankton is very low frequency. And so you expect that just the autoregressive nature of the time series allows you to have this prediction. How about the 2-year prediction? This is what it looks like. And again, the prediction scale goes a little bit down. It's 0.68, but it's still pretty high. We can now look at the 3-year prediction. And what we see, of course, that the scale continues to go down because now each of these points is essentially a 3-year lead prediction. We're predicting 3 years in the future, each one of these. And so it gets a little bit more challenging, but it's still pretty good. Now, one question that could arise is how robust is the estimate of the coefficients? Because in principle, you would want a model where these alphas are not very sensitive by which kind of training data set you use to estimate. And so let's look at this alphas. And so here now what is plotted are the alpha k's associated with the sea surface temperature forcing. And you can see here the essentially each dot is a different coefficient. And the gray lines are the different realization from the cross validation. So you see there's not a lot of spread. Actually, this is kind of quite robust. And from this, we find that there are 2 particular principal components that seem to carry the most predictive power. And this is PC1 and PC3, which in space are shown here. PC1 is connected to the El Nino signature with its extratropical teleconnections that have a PDO projection. And EOF3 is a PDO type pattern, which really occurs during times when you don't have a positive El Nino. So this is, if you like, a PDO residuals, which is dominated by extratropical dynamics. So this makes a lot of sense, and it's really useful too because it allows us to identify what forcing dynamics may be more important in carrying that predictability. So in general, I would say that the empirical dynamical model approach shows promise for forecasting ecological indicators in the CCS. And here we've applied it to the Nyctiphanes Simplex time series zooplankton. And again, here are the predictions that we did. However, of course, this is a simple flavor of what an empirical dynamical model is. In reality, with student Tong Su, we're developing some multivariate, more advanced empirical dynamical models. And this is an example of a slide from one of her talks showing the complex derivations. And we use these to forecast things also in space. And in fact, this is a prediction of sea surface temperature in the North Pacific for next winter of 2020. And this prediction, in fact, shows that the Gulf of Alaska marine heat waves seems to intensify. And these are the time series of this particular warm blob here in the North Pacific. This is the red time series. And the blue here is the prediction from this model, again, cross-validated, showing in 2020, the winter of 2020, a strong amplification. And with this, I thank you for your attention. And I hope this gave you a flavor of what empirical dynamical models can do also for forecasting ecological indicators in the California current. And thank you.